Hi students, this is Subramanian Gurti, your DSP teacher. Hope you have reached your home safely, and I also hope that you are staying at home itself safely. And I think it's time to restart the DSP course. So we will do it now in the online teaching way. I understand that some of you won't be having a very good bandwidth. So what I thought is, if the whole class is streamed through any of the existing tools, that you might face with some streaming problems. So what I thought is, we would rather go for a flipped classroom model. So what I'll be doing is, I'll be making the online lecture notes, and I would be uploading them into the YouTube, and I'll be sharing the links with you. You could go through them. You could download them at for example, if you have a very low bandwidth, you could, at a low bit rate, you could download it. You could let it buffer and download it completely, and then go through it at your own pace. And once all of you have gone through it, we'll have a meeting, maybe some Google meeting room or some other tools we'll explore as we move on, where you could pose your questions, concerns, and your doubts, which we will try to clarify during those meetings. In case still some of you, even if that bandwidth becomes difficult, what I plan to do is, I'll give you a slot during which you could either call me through the tools that we figure out, or you could call me by phone and get your doubts clarified. Okay, so we will move on with the classroom, this online video lectures. Okay, what I will do is, in this class I would make a quick review of what have been covered in the last couple of classes, as it has been quite some time now for you going through the DSP. Another thing I would try to do is, I would try to make these videos into small videos. I mean small in the sense around 15 to 25 minutes range, so that it becomes easier to download, and they will be also modular in nature. Okay, let's kick start. So this class, what I will do is, I will cover the transform analysis of LTI systems. This would be more of a revision of last few classes, 2-3 classes. Okay, what we will do right now is, the outline of the summary class would be, first I would be talking about what it means by analysis of these LTI systems. In particular, we will be discussing about the transfer functions of the LTI systems that have a rational form. This is what we would be discussing first, and then we would be talking about the causality and stability properties. Causality and stability, these properties of these rational systems is what we would talk about. And after that, I would talk about the inverse systems, and then again the causality and stability of those inverse systems. Causality and stability of those inverse systems. Okay, let it be H of Z. So here we will be talking about Hi of Z, and then inverse causality and stability of Hi of Z is what we would be discussing about here. And to conclude, I'll give you an exercise which you try to work it out after the class. Okay, this is roughly the overall outline of this review class, right? So anyway, most of these things are already discussed. So let's first start with how the rational form of a transfer function would look like. This, for example, let's call it as H of Z. This we have already derived in our previous classes, so I will not go through the derivation. Rather, let's spend some time on again getting an intuition for this form. K equal to 1 to m 1 minus ck z minus 1 by, in the denominator you have n terms getting multiplied. Okay, dk into z minus. This is the form of H of Z, right? Now let's make a quick analysis of this as well. So let's first start with this term, the numerator part of it. This is what we will go through it. What does this multiplication of these terms contribute to? As you know, this numerator part contributes to, you could rewrite the each of those terms as ck by z. That means again you take it the LCM, so that is z minus ck, which has a root at ck, and again in the denominator you have z, which means it contributes to poles, right? Poles by you got, yeah, anyway, let's start with the zeros first. Okay, where does it have zeros? The roots essentially will contribute to zeros of that transfer function. So where do you have those zeros? It contributes to zeros at ck, right? And this k varying from 0 to m. Sorry, this is 1 to m. Yeah, we are starting the index with 1, so this will be 1 to m. Similarly, it has poles. Poles are contributed by the denominator z that is coming. How many poles do we have here? So poles are there at z equal to 0, and there are m terms, so essentially you have here m poles, correct? Let's now come to the denominator part of it, right? And let's see what does it contribute to. Again, you write it dk into z minus 1, you could write it as dk by z. Okay, so that means you take again LCM, so that's z minus dk. So that means since it is in the denominator, this contributes to first poles at dk, and again these are there from 1 to n dk values, and again this by z would go to the numerator of it, so that contributes to zeros. You have zeros at z equal to 0, and there are n such zeros are there, correct? N zeros are there. Now assume that this m value is greater than n. That means that would eventually result these n zeros would get cancelled by n out of those m poles, and what you will be left with is m minus n poles at z equal to 0. You could do a similar analysis even when n is greater than m. So that's the form of representation. So that's the first form, rational form of h of z. Now let's take a look at the causality and stability part of this. So let's take a look into causality and stability of h of z. Okay, on what values does it depend? It depends on the poles of the given h of z. So what are the poles? The poles, where does it have poles? It has poles at z equal to 0, and also if at all m is greater than n, and essentially more importantly poles are there at dk. Those are the poles there. Okay, this side, let me erase this off. Okay, right. So the causal, first let's start with the causality part of it. So when do you, so what can you say for the cause, when will be the system will be causal? If you look at the ROC, right, absolute value of z should be greater than, or it should be outside the outermost pole. That's the condition, outermost pole. So how could you say about the outermost pole? Let's use some mathematical notation for this. Let's say let's call d max be the maximum pole. That essentially would be equivalent to you take max for all k values varying from 1 to n, and you take the absolute value of dk. That would give you d max. So if you call that as d max, For that system to be causal, what should happen now? Your absolute value of z should be greater than d max. Right? That's the condition for causality. Now let's move on to the condition of stability. So what should happen for the stability part? Well, all poles should be, for this function to be stable, all poles should lie inside the unit circle. Inside the unit circle. That's the condition for it, right? So if you call it as d max, you could in fact say it as d max is less than 1. That means all would be inside that anyway. And now if you want the system to be both causal plus stable, that's what the kind of system you are looking for. So if you want a system which is causal as well as stable, then what should happen? All poles should lie inside the unit circle and ROC should be outside the outermost poles. So both the above two conditions should get satisfied. That means all poles are inside the unit circle, and ROC is outside the outermost pole. Okay, what is that value here? This is anyway here, that's d max here, right? Yeah, those are the conditions. So that's as far as the causality and stability of HI of Z is concerned. Now let's discuss about the inverse systems now. Inverse of this system. Inverse system. Okay. Let's start with the block diagram of it. Let the system be characterized by H of Z. Let the input to that system be X of Z. Okay. When you say inverse of this system, if you concatenate with that system, which is in inverse of it, and if you look at the output of it, what should be the output? This also should result in X of Z. Then you call HI of Z as inverse system. So for the time being, let's call this output as Y1 of Z, right? Now what else? Let's call this whole transfer function. Okay, we could club them together. That would be equal, let's call it as G of Z, which should be equal to H of Z multiplied with HI of Z. Now what is the, so essentially this is X of Z you are getting. That's basically the output here, right? That output, let's call it as Y of Z. When this is equal to X of Z, then you call it as an inverse system. Then that is going to be an inverse system, correct? So how can we express Y of Z in terms of the input? That's nothing but G of Z into X of Z. This has to be equivalent to X of Z if at all this HI of Z represents an inverse system, which means G of Z must be equal to 1. That implies HI of Z is equal to 1 by H of Z. That's the inverse system. Let's write it now in the pole zero form of this inverse system, which we had earlier for H of Z. So if you write it in the pole zero form, how does it look like? Well, you had H of Z here, right? This is your H of Z here. So this you 1 by H of Z. So just simply make the numerator as the denominator and denominator as the numerator. So HI of Z would look like A naught by B naught, and in the numerator K varying from 1 to n 1 minus dk into z minus 1 divided by, in the denominator, k varying from 1 to m 1 minus ck g minus 1. What had happened here in terms of poles and zeros of h of z, if we have to express them in terms of the poles and zeros of h of z, essentially the poles of h of z have become the zeros of hi of z and zeros of h of z have become poles. So poles and zeros got exchanged, right? Before we move further about causality and stability, anyway we already did here the analysis in the frequency spectrum. Let's also do its analysis in the time domain. So let's call here input here in the time domain as x of n. Let this LTI system be characterized here by h of n. This be characterized with hi of n, and anyway this would be equal to y of n, and that being equal to x of n, and this is an inverse system. Now let's the equivalent of it in the time domain, let's call it as z of n here in the time domain. So then what would happen? How can we express y of n? Y of n is nothing but g of n convolved with x of n. What is it that we are supposed to get here? X of n, when it's an inverse system is concatenated with it. What does it mean? When will this happen? G of n is equal to delta of n. What does that mean? G of n in terms of h of n and hi of n, how can we write it? But it's nothing but the convolution of both of those things. So I could write here h of n convolved with hi of n would result in delta of n. This equation is an important thing in order to even make inferences about what should be the ROC of hi of z. Notice that for h of n convolution of hi of n to result in an impulse function delta in the discrete impulse, both should have some overlap here. So only constraint that is there in terms of ROCs of h of z and hi of z is that the ROCs of h of z and hi of z should overlap. That's what we get once we do this time domain analysis. This is how it's easy to look at what should be the ROCs. Again, there could be multiple possible ROCs which we have already discussed in the class, and anyway I will give you an exercise at the end of this lecture as well. Okay, that's as far as the inverse systems are concerned. Now let's take a look at causality and stability of hi of z. That's what we will take a look at now. Okay, let's take a look at causality and stability of hi of z. That's what we are going to take a look at. Well, let's make the interpretation in terms of h of z itself. So if you make an interpretation, again the interpretation is very similar to what we made here. For example, for h of z, all poles are inside the unit circle and ROC is outside the outermost pole. For hi of z also the conditions would remain the same. Okay, the same conditions gets applied there. But now if we want to make interpretation in terms of h of z, these poles are nothing but zeros of h of z. So what should happen here? All zeros of h of z should lie inside the unit circle. That's the condition, and ROC is outside the outermost pole anyway for the other things. Okay, now combining this both, if both h of z and hi of z have to be causal and stable, what should happen now? How could we ensure this? For that, what should happen? This is just a combination of both. So all poles and zeros of h of z should lie inside the unit circle. Okay. That's the condition to be satisfied, right? If both have to be causal and stable, this is the condition that needs to get satisfied, right? What next? So that's as far as the causality and stability of inverse systems and being both. Okay, we anyway had a much detailed discussion about various examples, but just as a warm-up and for a quick reminder of what we have already discussed in the class, I'd give you an exercise problem. You please do it before we have a conference call where we would try to address your questions, doubts and concerns. You please work it out and also make sure to revise by going through all the relevant slides that have been already shared, and this anyway this presentation will be also shared in the Moodle, so please go through them very carefully and then we will have a detailed discussion. So let's do this exercise problem. Okay, let your h of z, the rational function, has been given as 1 minus 0.4 into z minus 1 or 1 minus 0.2 into z minus 1, with the ROC of this function being greater than, anyway there is only one pole, it has to be, if it has to be stable in causal, it has to be greater than 0.2, right? Now given this, now you compute from this what would be the equivalent time domain discrete time sequence h of n, okay, and also compute all possible hi of z. Okay, as we discussed, there could be multiple all ROCs that have overlap with the above mentioned ROC are valid inverses for the system, and also there could be multiple ROCs here possible. So you find out all possible ROCs and corresponding, and also the corresponding hi of n values also you compute them. And also for all those inverse systems, you also comment whether they are causal, each one that is causal or not, whether it is stable or not. So comment also on causality and stability of those systems. Okay, what else? You could in fact also plot, okay, pole 0 plots here for each of them, and you could mark your ROCs here. Okay, you do all those things, right? Yeah, that's all for now. What I will do subsequently is I'll make some more video lectures in which I would discuss about any given system, how could we convert it into an equivalent system that is both causal and stable, although the initial system is not causal and stable. That's what the next lecture would be on. And at the end of that lecture, I would give you some exercises which you are supposed to solve on paper, and then you could take scan of them and then submit them in the Moodle assignment. And along with that, a very relevant MATLAB programming exercises will also be given, which will be part of your DSP lab that you are supposed to submit in the lab. Anyway, more details will follow, and that's all for now. Have a great day. Yeah, bye.